Good morning, everybody. Today we are jointly presenting a presentation on how we are approaching chiplets between ARM and ARM partner Alphawave in building solutions that Alphawave wants to target in the marketplace. My name is Sridhar Valluru. I'm Director of Product Management in the infra line of business at ARM. And Sue.
I'm the Principal Product Marketing Manager for the chiplet line at Alphawave Semi.
Cool. So our focus will be talking about the standardized approach to chiplet building, where we'll be focusing on how ARM is looking at the breaking down the systems to create a standardized interfaces, standardized architecture for building different chiplet components for a solution. And Alphawave will be taking that further to talk about how their silicon-proven IP is being composed along with ARM compute to build the overall industry solutions. So ARM's approach to chiplets or system building is standards-based. We leverage industry standards as much as possible, but we also look at where applicable, what ARM protocols need to be extended to build a system. So our view of chiplets is when somebody is building a monolithic die, because the die is too big or other reasons, they want to break that die into multiple dies. So the capabilities that they have on a monolithic SoC are the ones that we need to extend in a chiplet ecosystem. So we look at, from that viewpoint, in addition to supporting industry standards, we also look at what ARM needs to do to make it easier for partners to build their solutions. So we have extended the AMBA CHI as a chip-to-chip protocol or a die-to-die protocol. So that C2C can be applied both for socket-to-socket, chiplet-to-chiplet as well. And that enables partners to take the flexibility they had on a monolithic die to a chiplet ecosystem. We rely on industry standard transport protocols. So we support PCIe CXL PHYs as well as UCIe PHYs. But if there is a chiplet being built in-house and they want to take advantage of any proprietary SerDes, that is also possible in this ecosystem. The second standard that we are looking at is the chiplet system architecture. So when you are breaking down a system, a monolithic die into multiple dies, there is an architectural nuance of how system has to be partitioned and what are the different components that come into the picture. Here, the security is one of those components. I/O virtualization is the other one. Telemetry and other components that people were familiar with on a single die now have to be taken into the other die as well. So the sideband bus functions and all those capabilities have to be taken into account as well. So ARM is building what's called a chiplet system architecture for the ARM ecosystem today. And it's with partners like Alphawave, we're getting feedback to make sure that chiplet system architecture is compliant with, is enabling the solutions that partners have in mind. And the third standard that we look at, when you build these chiplets, none of these things are useful unless you can port software and build the end solution. So the third standard, the BSA and SBSA, and tag along the SBBR and SBMR, right? These standards make sure the standard software investment ARM has done is now extended to all these chiplet-based solutions. So any chiplet that are being built need to comply with these standards as well to make sure the software investments from all these companies and the ecosystem can be ported forward. So what are the benefits to the customers, right? The first benefit is because of the standardized interfaces, now you have the ability to build these two chiplets separately. I think that's one of the value propositions of chiplets, where applicable, you take the right technology node to build a particular kind of chiplet. So here, people have the ability to build the compute and the system die on different nodes and bring them together. With ARM compute subsystems, we have different performance points. So depending on the end solution, the solution builder can now go pick the appropriate performance point for that compute system and build the solution around it, right? So then you have the ability to go address all the way from one end of the spectrum where you're building a HPC AI or a large cloud server to the other end of the spectrum of an edge card, with the middle ground being your networking or 5G kind of solutions. Obviously, when you're building this chiplet separately, you have the ability to take the technology nodes and that make use of the technology that best serves that chiplet's purposes, cost, any advantages based on any technology nodes for power or those kind of things. I already mentioned the standard software. Building upon standards, basically all that effort that has been put in the last multiple years can be taken care of. And the biggest advantage here is time to market, because different components could be built and be ready on the shelf, so people can take advantage of what components are there, put them together, and build a solution. So ARM compute subsystem is a configurable set of compute block. We have spent quite a lot of effort in making sure all the integration nuances have been taken care of, making sure it is SBSA compliant so that the software stack is seamless across the spectrum. So these configurable blocks now can be built to address the different performance points. So customers have a choice in picking the right compute for the right solution that they want to build. And these support homogeneous chiplets, so that means the same compute chiplets can be packed together to build a server, or you can build a heterogeneous compute as well. So that gives you the option to build AI, ML, and other kind of solutions that are feasible in the marketplace. So as an example, we've had a CSS system which a pretty large customer took advantage of. They took the compute subsystem, built their accelerators around that particular compute subsystem, and were able to take advantage of the confidential compute and other capabilities that ARM compute was able to provide them. Not only that, they were able to take this compute subsystem, and within 13 months, were able to go from picking up the design to tape out. Right? I think that's a fairly big accomplishment considering the size of the solution that they were building. Coming back to what Alphawave is able to do with our compute, they have silicon-proven IP for their I/O and memory subsystems. And with the ARM compute and its standardized interfaces, now they're able to mix and match those different kinds of system components, memory and I/O, to build solutions that can address multiple markets. Right? So their targets, they're looking at 5G, 6G infrastructure markets, build cloud computing solutions, as well as edge computing solutions. So just to summarize from a standardization point of view, there are Chai C2C basically gives you a layered architecture, so it's the same interface that you can use. The same capabilities that are available on die, you're able to take it off die as well. It gives you the link optimization to go over standard transport. It provides you the ability to take the capabilities from one on the compute die to the component die as well. Chiplet system architecture, because it defines the different chiplet types, it creates that interoperability that's required between the two independently developed chiplets and enables reuse. Okay. With that, I'll hand over to Sue to continue the.
Thank you very much, Sridhar. So now we're going to be looking at the solutions that ARM and Alphawave Semi provides for data center challenges as we deploy AI at scale in the data center. So two of those key items are custom compute and connectivity. On the left side, we're looking at custom compute, where there's really no one single piece of hardware fits all, because we have different types of system and application needs, such as compute versus network bandwidth needs, or high sensitivity to latency, or a need for more memory bandwidth versus memory density capacity. So it's really difficult to serve all the classes of LLM models with a single system design point for hardware. And then on the right-hand side, we're looking at connectivity in the data center. So That chart on the right-hand side shows that almost 40% of the time, the LLM or average AI ML model will sit on the network, moving from processor to processor. And connectivity is really key, so let's look at how AI is connected in the data center. Inside the front-end network, behind the servers are the AI ML clusters connected over to the back-end network. And the back-end network has processors that can access each other's memories seamlessly. On the front-end side, the incoming compute requests will make that rise and fall with those incoming requests. So if there's any bad link or a packet drop and loss in connectivity, we're going to have a less robust network, and we are going to lose XPU, GPU, CPU resources, as well as slow down those training jobs. So those two factors, connectivity and hardware solutions, we will look at the solutions in the next slides to help here. So this is a full AI connectivity suite. In the middle there, the CPU, that's where ARM and Alphawave Semi collaborate together to produce a Neoverse compute chiplet. And this has AMBA Chai C2C over the PCIe and UCIe interconnects over to the accelerator side. On the front end, it has Ethernet cards with peripheral interconnects over to PCIe and low latency memory pooling through CXL. On the back end network, there's Ethernet, and we're moving up towards Ultra Ethernet, very similar to NVIDIA's InfiniBand. And also on the XPU or accelerator links, we'll be moving towards UA link, very similar to NVIDIA's NVLink. So these are foundational IPs that Alphawave Semi provides for connectivity, the PHY and controller subsystems, as well as HBM. And so we are ushering in a new era of semiconductors with chiplets. Alphawave Semi has standard off-the-shelf chiplets as well as custom chiplets. Our off-the-shelf chiplet portfolio is made up of I/O chiplets as well as the compute chiplet in collaboration with ARM. And then derivatives of that are custom. We also can do optical chiplets or high bandwidth memory chiplets, as well as high density capacity memory chiplets. And we apply the latest adoption of UCIe Rev 2.0 onto our chiplet solutions. So Alphawave Semi incorporates ARM AMBA interconnect standards as part of that ecosystem that we are in. And we also are in the UCIe working groups as well as OCP. And as UCIe has recently gone to 2.0 in August, we're seeing the advancement in the packaging. So we are also moving towards 3D bonding. And that's hybrid bonding over SOIC-X, face-to-face bonding. We also have expertise in packaging across 2.5D packaging. We have silicon interposer, as well as RDL and bridge solutions across multiple foundries and OSATs. And we are also a TSMC VCA as well. So we provide all of these silicon-proven IP subsystems to provide the connectivity in our chiplet portfolio, as well as the compute chiplet that we collaborate on with ARM. And we are moving on the very mature process nodes from 7 nanometer on down to the angstrom node. We enable these across multiple foundries. we're moving towards the 224 gig, as well as 1.6T Ethernet, Ultra Ethernet and UA-Link, as I had mentioned, and also PCIe Gen 7, 128 gig. Also on UCIe fronts, we are moving higher, 32 gig plus on the latest standard, but moving higher as we see that go up, and moving towards the hybrid bonding, as I had mentioned, and that enables much higher bandwidth density, even though that data rate comes down because of that pitch falling less than 10 microns. And we are also enabling silicon-proven 9.6 gig on our HBM3E fine controller subsystems. And we are moving towards the fork in the road of JEDEC compliant, as well as custom HBM4. So I don't have a lot of time left, but please come and see us at the booth, where we're showing at the ARM booth and Innovation Village our UCIe over advanced package silicon interposer at 24 gig, and we have these available over 2D as well as 2.5D, and as I mentioned, moving towards 3D. So please come and ask us any questions at our booths. This is our industry first multi-protocol I/O chiplet. We call this the Alpha Chip 1600-IO. It has reconfigurable 112 gig SerDes on one end, and on the other end it has the PHY and controller subsystems. We can move Ethernet PCIe and CXL traffic through that at 1.6 terabits per second. With medium reach for optical or extra long reach for Ethernet applications. And the operational modes in that, we can do Ethernet only, we can do PCIe only, or mixed modes of PCIe and Ethernet. And starting with the 1.6 terabit per second I/O, which is off the shelf, we employ that on standard package for low cost. And then moving to the future generations, we can enable UCIe interfaces to just switch out to the next generation of a 3.2 terabit per second I/O, and that can be enabled with UA-Link, PCIe Gen 7, Ultra Ethernet. And any derivatives of those I/O chiplets, we can make custom in advanced package with custom proprietary UCIe streaming protocol with retimers or JESD deterministic latency. So all different types of different I/O chiplets that we can create as custom derivatives as well. So we leverage ARM's N3 Neoverse compute cores onto our silicon solutions, along with Alphawave Semi's silicon-proven IPs to have a combined solution of AI silicon solution compute chiplets. And at the very top, where the ARM Neoverse CSS chiplet is shown, that is our collaboration with ARM on that compute chiplet. We enable that as a chiplet or monolithic die through the UCIe and PCIe interface. That has the PCIe CXL enablement on the north side and memories on the east and west side. And also it attaches on the south over to an accelerator chiplet. Any UCIe interface can attach our I/O chiplets for scale up and scale out through PCIe and Ethernet. And if you stop by our booth, we are also showing our energy efficient accelerator cards, the near term and future term versions. The UCIe chiplets for the I/O chiplet can be replaced there with the next generation, as I mentioned, for remote accelerators or back-end Ethernet switches, and that enables optical as well as copper connectivity, and a future generation card would enable co-packaged optics and co-packaged copper as well. So please stop by our booth to see that and ask any questions. And this is my last slide, the lessons that we've learned and the challenges that we've met doing the I/O chiplet. We know that PPA is a critical need because as we disaggregate from monolithic dies, we are creating redundant circuitry for those dies to talk to each other. So we really need low power, latency, and area, but high bandwidth throughput at the same time. We want to enable standard interfaces so that when we plug in a chiplet, it can also talk to the other side through the same protocol. And also, there isn't one size fits all, so we're seeing very many different types of use cases, different form factors, number of lanes, et cetera. And lastly, we are enabling quick time to market with ARM and Alphawave Semi with the pre-verified and pre-configured CPUs from ARM, as well as the silicon-proven IPs from Alphawave Semi, and we enable that with our software, firmware, and hardware kits that we provide. So we thank you very much for listening. Please stop by at our booth. We provide silicon IP proven for our chiplets, both custom and standard off the shelf, and we provide connectivity products as well. Thank you.